So let's start by basically looking at this very nice list of internal data structures for the kernel. You can actually go to this link. They have done a pretty good job in linking to different web pages that basically describe some of the internals of the kernel data structures. I'm not going to go through this list, but I'm rather going to start off with talking about a few of them. Hopefully some of them can help you. So what I will cover are linked lists, queues, maps, binary trees, and something that is called R hash tables. And these are basically 5 data structures that you can probably use for or basically reuse some parts of them to implement your key value store. So linked lists, you probably have studied them. I'm going to go through them pretty fast so that you remember. They are basically data structures that allow you to store and manipulate a variable number of elements, and that is basically by you can have, they are not like arrays, for example, where most arrays you need to specify how large they are, but rather they are dynamic, so you can add more data to them or remove more data from them. And the elements that you are operating on adding and removing and searching for are typically called nodes. And this is the most commonly used data structure used in inside the kernel by far. Can you think of a reason? So, and can you also think about the implications of having linked lists as the most used data structure in the kernel? I'm asking these questions to basically measure how you guys remember your data structures course. Okay. So the main reason that this is basically used in Linux that much is that, well, we do not really know how many threads you will end up starting. For example, we do not know how many users will be using the system. We do not know how many files you will store in the system, and so on and so forth. So what you need is that you need the data structure that you can extend. And since memory is not allocated necessarily to occupy contiguous regions, because basically you start allocating some memory for some threads, and then for 3 days you're not really adding any threads, and then you start adding new threads. So you do not really have contiguous regions in the memory, which has implications on your performance. Because, well, basically you need to jump between different memory locations, and as long as these memory locations are in the same if they are near each other, it's better than jumping to memory, for example, that is connected by a bus outside of the chip. Okay, but that's hardware. So the way we connect the different elements in the linked list is through basically a link, and these links are sort of pointers to where your next memory location is, i.e. your next element is. And they basically, each link is just a pointer to the next element in your linked list. This is what is called a doubly linked list. So you do not just have the pointers pointing forward, but you also have them pointing backward, so that you can go, if you're at, for example, node 1, you can go to node 2 easily. Sorry, if you are at node 2, you can go to node 1 easily, but you can also go to node 3. So you have 2 ways to traverse the linked list, and this is what is called a doubly linked list. Then you have what is called a circular linked list, where, well, you still, here we do not have the backward pointers, but we just have a loop such that the last node in your linked list is basically also connected to the first node in your linked list. So you have a circle that you rotate along. And then there is a circularly doubly linked list, which is basically a linked list where you have both a way to go forward, so from node 2 to node 3, but from node 3 to node from node 2 to node 1 also. But then when you approach the end, then you can go forward by just going to node to the first node in your linked list. So suppose this is node number 100, for example, and then you can go to node 1. But also you can go backward from node 1 to node 100. So it's circular basically. And this is the Linux implementation essence. I mean, we want a doubly circular linked list. When do we use a linked list? Linked lists are very good when you're accessing data sequentially, or there is some structure in the way you access data. So you go from thread 1 to thread 2 to thread 3, for example. But they are very bad when you are accessing data in random. So if you try to just pick a random element in the linked list, this can be pretty costly. And the easiest way to move through the linked list is basically by using your pointers, of course. So the Linux implementation of linked lists is different, and the idea is, well, it's not entirely different. It's just the way that they have decided to implement it. So instead of having a class, for example, or an object that is called linked list, they have decided to basically provide the means to convert any structure into a linked list. So you do not call a linked list, for example, header. You do not include linked list.h, for example, but you do something else. You basically have Linux taking care of this mapping between different structs by just including very basic primitives that you would need for converting a struct to a linked list. And there is a historical background to this. If basically everybody implemented his own / her own linked list, taking into account just what their own use case is, but never looking at the big picture. So they basically got together, sort of, and decided that, well, that enough is enough. We need basically to unify this. We shouldn't have 100 implementations of a linked list. And this is something that plagues the Linux kernel implementation, actually. Some of you have already noted that there are multiple files that do roughly the same thing, and they are basically trying to improve on this because, well, the kernel is bloated right now. So this is how they implemented. You implement a linked list basically, and the implementation is in well, I can hardly see because my screen is very far away, but let me just try to. I'm not sure if you guys can see it. Okay, so anyway, so the implementation is basically, I'm just getting closer to my screen, in lists.h, and I have a very far away screen. So the implementation is in lists.h, and there you basically have a very simplistic implementation. This is basically what you initialize a list with, a linked list with. You just include this. You use this to basically make the pointers, and that's it, and add it to any struct. And then Linux, the kernel itself, lists.h, takes care of all the internals of actually implementing a list. Let's take a look at how you actually do this in code. Well, you basically have, suppose you have a struct that you call Fox, and that struct that is called fox. You want to basically have a linked list of foxes, for example. So you have struct fox, and you have the tail length of your fox, like the actual biological tail, not CS tail. So length in centimeters of tail, the weight of the fox, and is that fox beautiful or not. Okay, and then once you do that, you include this struct list head list, and this is basically something that is defined in lists.h, and it's basically how you make your linked list happen. So you include struct list head list, and then you basically set up list.next to point to the next element. So you basically have struct list head list. I mean, this you could call linked list. You can't call anything else. It's probably bad naming here, but let's call it fox list. So you can then add the pointers to fox list.next and fox list.priv to basically point to next and previous elements in your linked list. And you have a list add method that adds a new node to an existing linked list. Okay, so you can actually do this addition by just using list.add.